NASA's Mars Reconnaissance Orbiter (MRO) has begun extra stargazing to help the space agency accomplish advances in Mars exploration over the next decade. The spacecraft already has worked more than double its planned mission life since launch in 2005. NASA plans to keep using it past the mid-2020s. Increased reliance on a star tracker and less on aging gyroscopes is one way the mission is adapting to extend its longevity. Another step is wringing more useful life from batteries. The mission's extended service provides data relay from assets on Mars' surface and observations with its science instruments, despite some degradation in capabilities. We know we're a critical element for the Mars program to support other missions for the long haul, so we're finding ways to extend the spacecraft's life, said MRO project manager Johnston of NASA's Jet Propulsion Laboratory, Pasadena, California. In flight operations, our emphasis is on minimizing risk to the spacecraft while carrying out an ambitious scientific and programmatic plan. JPL partners with Lockheed Martin Space, Denver, in operating the spacecraft. In early February, MRO completed its final full swap-over test using only stellar navigation to sense and maintain the spacecraft's orientation without gyroscopes or accelerometers. The project is evaluating the recent test and planning to shift indefinitely to this all-stellar mode in March. From MRO's 2005 launch until the all-stellar capability was uploaded as a software patch last year, the spacecraft always used an inertial measurement unit containing gyros and accelerometers for attitude control. At Mars, the orbiter's attitude changes almost continuously with relation to the Sun and other stars as it rotates once per orbit to keep its science instruments pointed downward at Mars. The spacecraft carries a spare inertial measurement unit. The mission switched from the primary unit to the spare after about 58,000 hours of use, when the primary began showing signs of limited life several years ago. The spare shows normal life progression after 52,000 hours, but now needs to be conserved for when it will be most needed, while the star tracker handles attitude determination for routine operations. The star tracker, which also has a backup on board, uses a camera to image the sky and pattern recognition software to discern which bright stars are in the field of view. This allows the system to identify the spacecraft's orientation at that moment. Repeating the observations up to several times per second very accurately provides the rate and direction of attitude change. In all-stellar mode, we can do normal science and normal relate, Johnston said. The inertial measurement unit powers back on only when it's needed, such as during safe mode, orbital trim maneuvers, or communications coverage during critical events around a Mars landing. Safe mode is a precautionary status the spacecraft enters when it senses unexpected conditions. Precise attitude control is then essential for maintaining communications with Earth and keeping the solar array facing the Sun for power. To prolong battery life, the project is conditioning the two batteries to hold more charge, reducing demand on the batteries, and is planning to reduce the time the orbiter spends in Mars' shadow when sunlight can't reach the solar arrays. The spacecraft uses its batteries only when it is in shadow, currently for about 40 minutes of every 2-hour orbit. The batteries are recharged by the orbiter's two large solar arrays. The mission now charges the batteries higher than before to increase their capacity and lifespan. It has reduced the draw on them, in part by adjusting heater temperatures before the spacecraft enters shadow. The adjustment preheats vital parts while solar power is available, so the heater's drain on the batteries, while in shadow, can be reduced. The near circle of MRO's orbit stays at nearly the same angle to the Sun as Mars orbits the Sun and rotates beneath the spacecraft. By design, as the orbiter passes over the sunlit side of the planet during each orbit, the ground beneath it is about halfway between noon and sunset. By shifting the orbit to later in the afternoon, mission managers could reduce the amount of time the spacecraft spends in Mars' shadow each orbit. NASA's Mars Odyssey spacecraft, older than MRO, successfully did this a few years ago. This option to extend battery life would not be used until after MRO has supported new Mars mission landings in 2018 and 2021 by receiving transmissions during the lander's critical arrival events. "We are counting on Mars Reconnaissance Orbiter remaining in service for many more years," said Michael Meyer, lead scientist of NASA's Mars exploration program at the agency's Washington headquarters. "It's not just the communications relay that MRO provides, as important as that is. It's also the science instrument observations. Those help us understand potential landing sites before they are visited and interpret how the findings on the surface relate to the planet as a whole." MRO continues to investigate Mars with all 6 of the orbiter's science instruments, a decade after what was initially planned as a 2-year science mission, to be followed by a 2-year relay mission. More than 1,200 scientific publications have been based on MRO observations. Teams operating the 2 instruments named most often in research papers the High-Resolution Imaging Science Experiment, HIRISE, camera and the Compact Reconnaissance Imaging Spectrometer for Mars, CRISM, Mineral Mapper are dealing with challenges but are ready to continue providing valuable observations. For example, some HIRISE images taken in 2017 and early 2018 show slight blurring not seen earlier in the mission. The cause is under investigation. The percentage of full-resolution images with blurring peaked at 70% last October, at about the time when Mars was at the point in its orbit farthest from the Sun. The percentage has since declined to less than 20%. Even before the first blurred images were seen, observations with HIRISE commonly used a technique that covers more ground area at half the resolution. This still provides higher resolution than any other camera orbiting Mars, about 2 feet, 60 centimeters per pixel, and little blurring has appeared in the resulting images. Using 2 spectrometers, XRISM can detect a wide range of minerals on Mars. The longer wavelength spectrometer requires cooling to detect signatures of many minerals, including some associated with water, such as carbonates. To do this during the 2-year Prime Science mission, XRISM used 3 cryocoolers, one at a time, to keep detectors at -235 Fahrenheit, -148 Celsius, or colder. A decade later, 2 of the cryocoolers no longer work. The last has become unreliable, but is still under evaluation after 34,000 hours of operation. Without a cryocooler, XRISM can still observe some near-infrared light at wavelengths valuable for detecting iron oxide and sulfate minerals that indicate past wet environments on Mars. The context camera, CTX, continues as it has throughout the mission, adding to near-global coverage and searching for changes on the surface. The shallow radar, SHARAD, continues to probe the subsurface of Mars, looking for layering and ice. Two instruments for studying the atmosphere, the Mars Color Imager, MARCI, and Mars Climate Sounder, MCS, continued to build on nearly 6 Mars years, about 12 Earth years, of recording weather and climate. The University of Arizona operates HERISE, which was built by Ball Aerospace and Technologies Corporation. Boulder, Colorado. The Johns Hopkins University Applied Physics Laboratory, Laurel, Maryland, leads MRO's XRISM investigation. The Italian Space Agency provided SHARAD. Malin Space Science Systems, San Diego, built and operates CTX and MARCI. JPL, a division of Caltech in Pasadena, California, manages the MRO project for the NASA Science Mission Directorate in Washington and leads the MCS investigation.